The observable universe refers to the portion of the universe that we can observe and study using telescopes and other instruments. However, this capability is limited because light, the main source of information about the universe, can only travel at a finite speed. As a result, we can only observe objects and events that are at a certain distance from us. We cannot directly see objects or events that occurred long ago in the past. The diameter of the observable universe is estimated to be approximately 93 billion light-years, which is much larger than the estimated age of the universe, which is estimated to be 13.8 billion years. The discrepancy is because the expansion of the universe has caused objects that were once close together to move away from each other, and light from those objects has required more time to reach us. Overall, the universe is a vast and fascinating space, but there is much more we do not know about it. However, with the use of NASA's James Webb Telescope and other scientific instruments, we can continue to learn more about the structure, composition, and history of the universe, as well as various phenomena. Join us as we discover the massive structure that the telescope just made contact with at the far reaches of the universe. If you are interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel, be sure to like this video, and turn on the notification bell. What lies beyond the observable universe? To reach the far reaches of the observable universe, we would need to develop transportation methods that would allow us to transcend space and time, such as using a distortion engine or wormholes. This concept has long been the subject of debate among scientists, some of whom believe that they are simply impossible and that they contradict the idea of faster-than-light speed travel. The feasibility of both possibilities, faster-than-light travel and the use of advanced technology beyond the reach of current human intelligence, is a subject of intense debate. Even if they were theoretically possible, it would require technological advances in machinery that are clearly beyond our current capabilities. The theory of cosmic inflation posits that the total size of the universe is at least 10 to the power of 23 times larger than the observable universe. This number is so vast that it is incomprehensible to the human mind. Since we cannot see or measure the unobservable part of the universe, we have no way of knowing with certainty what lies beyond its limits. However, that does not mean that we cannot develop theories based on the information we have gathered from distinct galaxies. And this is where NASA plays an important role. NASA, in collaboration with other space agencies and research institutions around the world, has made numerous significant contributions to our understanding of the universe. Even before the James Webb Telescope became operational, NASA had already published images of the ultra-deep field obtained with the Hubble telescope. When the James Webb Telescope made its debut, it was tasked with observing the most distant galaxies ever recorded. These images revealed the presence of numerous galaxies shining in the distant cosmos, apparently as they were millions of years after the Big Bang occurred approximately 13.8 billion years ago. The expansion of the cosmos causes the stretching of light to red wavelengths, which allows the James Webb Telescope to detect infrared light. This has allowed us to observe galaxies forming in the early stages of the universe's history. The James Webb Telescope has made observations of several fields of distant galaxies, allowing scientists to study the rate at which they formed in the early universe. These data revealed the existence of a significant population of galaxies that were forming stars in the early stages of the universe. The discoveries are truly fascinating and thought-provoking. For a long time, humans have contemplated the possibility that we are alone in this vast universe. However, these new determinations within the observable universe lead us to believe that there must be millions of galaxies in the unobservable part of the universe. This idea is truly shocking and awakens a sense of awe and wonder about the vastness of the cosmos. Are there extraterrestrial beings somewhere in the universe? The likelihood of life beyond Earth has never been more compelling, leading us to consider the possibility of the existence of extraterrestrials. There are numerous planets outside our solar system known as exoplanets, which have been discovered using techniques such as the transit method and the radial method. Some of these exoplanets may have Earth-like characteristics and harbor life. This theory has been supported by another discovery made thanks to the James Webb Telescope related to the exoplanet WASP 96b. This planet is located outside our solar system, and its light spectrum reveals something surprising: the presence of water molecules. In addition, the spectrum also shows signs of haze and clouds, which were not previously thought to exist on a habitable planet. Based on the habitable environment found elsewhere in the universe and considering the advances in the search for exoplanets, it is difficult to rule out the possibility that alien beings exist beyond our planet. Although we do not yet have conclusive proof, discoveries and evidence suggest that the existence of extraterrestrial life is a fascinating possibility. What about the multiverse in relation to the vastness of the observable universe? Let me tell you, the possibilities are endless. The concept of the multiverse, also known as the many worlds interpretation, is a theoretical idea in physics and philosophy that suggests the existence of multiple parallel universes or dimensions beyond our own. The multiverse is mainly discussed in the context of quantum physics, which deals with the behavior of tiny particles such as atoms and subatomic particles. According to some interpretations of quantum physics, the act of observation can cause a quantum system to collapse into a single state. However, in the many worlds interpretation, the act of observation simply causes the system to split into multiple states, each representing a different outcome. It is important to note that the idea of the multiverse remains highly speculative and is not yet supported by conclusive evidence. It is therefore difficult to state with certainty whether it is a valid concept or not. Some scientists and philosophers find the idea of the multiverse intriguing and potentially useful in explaining certain phenomena, while others are skeptical about its validity. Given that we do not know what lies outside our universe, the possibility of the existence of a multiverse remains as valid as famous thought experiments like Schrödinger's cat or the nature of darkness. It is a concept that arouses fascination and reflection and requires further research and evidence to be confirmed. Thus, the phenomenon known as dark flow exists. The question is complex and raises intriguing issues. Dark flow emerged in 2008 as a possible explanation for the observation that some galaxy clusters appear to be moving faster than expected based on the distribution of matter in the universe. The concept of dark flow suggests that these galaxy clusters may be influenced by some form of dark matter or dark energy that pulls them in a specific direction. However, the existence of dark flow remains controversial and has not been accepted by the scientific community at large. Some studies have suggested that dark flow may be real and could be caused by the presence of a massive structure in the universe that exerts an attraction on galaxy clusters. However, other studies have failed to confirm the existence of dark flow and have proposed that the observed motion of galaxy clusters could be the result of other factors, such as systematic errors in the detected galaxies. While some studies suggest its possible existence, we cannot state with certainty its presence outside the observable universe. More research and evidence are needed to better understand this intriguing phenomenon. In exploring the nature of the universe, it's crucial to understand the concept of cosmic background radiation. This is the faint glow left over from the Big Bang and serves as a crucial piece of evidence for the Big Bang theory. Discovered in 1965 by Arno Penzias and Robert Wilson, this radiation provides a snapshot of the universe when it was only about 380,000 years old. This radiation is remarkably uniform but does contain slight fluctuations that correspond to the density variations that eventually led to the formation of galaxies and large-scale structures. The cosmic microwave background, CMB, radiation has been instrumental in refining our understanding of the universe's age, composition, and development. One of the significant challenges in modern cosmology is understanding the nature of dark matter and dark energy. Dark matter is thought to constitute about 27% of the universe, yet it neither emits nor absorbs light, making it invisible and detectable only through its gravitational effects. Dark energy, which makes up roughly 68% of the universe, is even more enigmatic. It is hypothesized to be responsible for the accelerated expansion of the universe. This expansion was first observed in 1998 through the study of distant supernovae, which showed that the rate of expansion was increasing over time. Understanding these two components is crucial for a comprehensive understanding of the universe's fate. One intriguing aspect of the universe's expansion is the concept of the Big Freeze, or heat death. This theory suggests that as the universe continues to expand, it will eventually reach a state where stars burn out, galaxies drift apart, and the universe becomes increasingly cold and dark. This scenario is based on the observation that the rate of expansion is accelerating, driven by dark energy. Alternatively, some theories propose a big crunch, where the expansion might eventually slow down and reverse, leading to a collapse of the universe into a singularity. The ultimate fate of the universe is still a topic of active research and debate. In addition to these theoretical predictions, cosmologists use observational data to test their hypotheses. The Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, are examples of large-scale surveys that map the distribution of galaxies and other cosmic structures. These surveys help scientists to probe the large-scale structure of the universe and understand how it evolved over time. By analyzing the distribution of galaxies and the patterns of cosmic structure, researchers can infer the properties of dark matter and dark energy. Another frontier in cosmology is the study of gravitational waves. Predicted by Einstein's theory of general relativity, gravitational waves are ripples in spacetime caused by massive accelerating objects, such as merging black holes or neutron stars. The first direct detection of gravitational waves by the LIGO Observatory in 2015 confirmed Einstein's predictions and opened a new observational window into the universe. Gravitational waves provide a unique way to study phenomena that are invisible through traditional electromagnetic observations, offering insights into the most violent and energetic events in the cosmos. Astrobiology, the study of life in the universe, intersects with cosmology and planetary science. The search for extraterrestrial life involves studying extreme environments on Earth, such as hydrothermal vents and acidic lakes, to understand how life might survive in harsh conditions elsewhere. Missions to Mars, like NASA's Perseverance rover, are designed to search for signs of past microbial life and to collect samples that might be returned to Earth for further analysis. Additionally, telescopes like the James Webb Space Telescope aim to analyze the atmospheres of exoplanets for biosignatures that could indicate the presence of life. The study of exoplanets has seen significant advancements in recent years. Techniques like transit photometry, which measures the dimming of a star as a planet passes in front of it, and radial velocity, which detects the wobble of a star due to the gravitational pull of an orbiting planet, have led to the discovery of thousands of exoplanets. Some of these planets are located in the habitable zones of their stars, where conditions might be right for liquid water to exist. The characterization of these exoplanets' atmospheres and climates is crucial for assessing their potential habitability. The concept of habitability extends beyond Earth-like conditions. Researchers are also exploring the possibility of life in subsurface oceans of icy moons, such as Europa and Enceladus, which may have conditions suitable for life. Missions to these moons, like NASA's upcoming Europa Clipper mission, are designed to investigate their ice-covered oceans and assess their potential for hosting life. In the realm of theoretical physics, string theory and quantum gravity are actively explored to reconcile general relativity with quantum mechanics. String theory proposes that fundamental particles are not point-like but rather one-dimensional strings vibrating at different frequencies. This theory aims to unify all fundamental forces and particles into a single framework. Quantum gravity, on the other hand, seeks to describe the gravitational force within the quantum mechanical realm, potentially offering insights into the nature of spacetime itself. The concept of time is also a profound aspect of cosmological studies. In general relativity, time is intertwined with space into a four-dimensional spacetime fabric. The effects of gravity on time are evident in phenomena such as time dilation, where time moves slower in stronger gravitational fields. This effect has practical implications, such as in the Global Positioning System, GPS, where satellites must account for relativistic time differences to provide accurate positioning information. As we look to the future, the advancement of space technology will play a crucial role in expanding our understanding of the universe. The development of next-generation space telescopes, such as the upcoming Extremely Large Telescope, ELT, and the Square Kilometer Array, SKA, promises to provide unprecedented details about the cosmos. These instruments will enable us to peer deeper into space and further back in time, potentially uncovering new aspects of the universe's formation and evolution. Additionally, international collaborations, such as the International Space Station, ISS, and various space missions conducted by different space agencies, exemplify the importance of global cooperation in advancing space science. These collaborative efforts help pool resources, expertise, and data, leading to more comprehensive and accurate scientific discoveries. In conclusion, The universe remains one of the most captivating subjects of study, with countless mysteries yet to be solved. As technology advances and our observational capabilities improve, we are continually expanding our knowledge of the cosmos. The interplay between theoretical predictions, observational data, and experimental research drives our quest to understand the universe's origins, structure, and ultimate fate. With each discovery, we move closer to answering some of the most profound questions about our existence and the nature of the cosmos.